AMC live prep session. AMC live. Oh wait, it's all in caps. We're live. Live
AMC
prep
live.
session.
Alive. Get rid of MC and then we're alive.
Get rid of the math counts and we're live.
Yeah, get rid of. Okay. That's so cool.
Alrighty. So, how is everybody doing today? How are we feeling? Anything interesting happen? Oh, I actually like this. So I'm going to ask you guys, what's the coolest thing you've learned this week? What's the coolest thing you've learned this week? And make sure, I still see a lot of people, actually, I don't know what, you guys are doing good. I just realized. I'm like, oh, I'm getting DMs. No, I'm not. I am chat relay, so of course I'm getting DMs.
Wait a moment.
You didn't hear anything.
Okay. Wait, step functions. Wow, step functions.
Step functions? Oh, I didn't mean math. It could be anything, but
wow. Okay, wait. People like math.
Yes, you're alive. That's good to know.
Programming, that's good.
Aiden, what's the coolest thing you've learned this week?
Me?
Or maybe in the recent time?
Okay.
If you stay quiet in class, you're more likely to be called on. That's an unfortunate lesson to learn.
That is true. Oh my god. If you're loud in class, okay. If you're loud in class, the teacher won't call on you. But then again, you're being loud already, so that like defeats the point if you don't want to get called on. So
yeah, but hey, in our classes, we do that to try to make sure everybody gets a turn to talk. But
yes,
it's all voluntary. We won't force you to talk if you don't want to. You learn perfect pitch. That's crazy. I have a TA friend. We have a TA friend who's
oh my
perfect
gosh.
pitch. We have a TA friend who knows perfect. Who like what is it? Is it has perfect pitch, right? That's pretty cool.
Pitch, yeah,
so we listen to songs, and then she like tells me all the notes. But okie dokie. So mashed potatoes look like vanilla ice cream. I mean, I wouldn't be disappointed with either, but I think it would suck if I expected mashed potatoes and got ice cream, or expected ice cream but got mashed potatoes. They're two different ballparks. Alrighty. You ready to hop into it, Aiden?
Sure.
All right. Quick introduction. Aiden, some of you guys have probably seen him before. Super cool, super good at math. He's a freshman, not an incoming freshman. School's already started. He's a freshman, already in JMO honorable mention in previous years, and also represented Texas at Math Counts Nationals, and likes listening to K-pop, doing biology in his free time, all that cool stuff.
Okay, yeah. I also have to introduce Eddie. Eddie is also super awesome. He's a senior now. Oh my goodness.
Oh no.
I originally thought he was a sophomore last year, but he's a senior now. And basically, Eddie is really good at math as well. He made Amy multiple times, and that's like 5%. I'm sure if y'all are here for AMC, y'all know what Amy is. It's pretty cool. And then he's also he was the Ohio Math Gun State Champion. Too old for that now. But in middle school, he was the Math Guns Ohio State Championship. Also, Eddie can speak a lot of different languages, like Spanish and Japanese. Those are some languages he can speak. Awesome.
No, all right, just learning. But without further ado, let's actually get started with the AMC. So I think today's is the 2021 AMC 10B. So we're going to be taking a few problems from there. And without further ado, I'll throw it to you, Aiden, for the first one.
All right. Okay, first one. Let's see. Warm-up problem or no warm-up problem? I don't know. Hopefully this one isn't too bad. So an inverted cone with base radius 12 centimeters and height 18 centimeters is full of water. So an inverted cone, I could draw that real quick. It's basically like those cups you get at those outdoor tennis courts, if you've seen those. But it's just an inverted cone filled with water. The important information here is 12 centimeter base radius. So this thing is 12 centimeters. And then height 18 centimeters full of water. So this might have to do with the volume. 18 cm. The water is poured into a tall cylinder whose horizontal base has a radius of 24 centimeters. What is the height in centimeters of the water in the cylinder? So it's not a cone anymore. Not a cone. We're looking at a cylinder now. And it's a little bit fatter than the cone. So poured into a tall cylinder. It says it's tall, so I'm going to assume that the height is pretty big. And then the base radius is 24 centimeters. We know that. And then if we pour all the water in here into here, we want to find the height here. So of course, volume is going to play a big role in here. Does anyone know the volume formula for a cone? Because the logical first step is to find how much water is actually in this cone and then dump it in here and then figure out how much water is in here and then how much height there has to be. Let's see. 1/3 pi r squared h. Yeah,
I think
pi.
a few people are getting confused with the cone, sorry, the sphere.
Oh, yeah.
So be careful there.
I was looking at that and I was thinking, wait, 4/3 is somewhere right. But yeah, 4/3 is for a sphere. So for a sphere, we have 4/3 pi r cubed. And then for a cone, though, we have 1/3 pi r squared h. And then for a cylinder, that is pi r squared h. So basically, we don't actually have to find the water here, actually, because we can just use some sort of ratios. So if we look at this a little bit closely, we're dumping the volume of our cone into the cylinder. So from here to here,
Hey guys, if you could make sure real quick that you guys are muted in the main room, so that way we can stay quiet there.
Yeah, make sure to
yes.
mute yourself.
Yes.
All right, back on track. But from here to here, we have the 12 centimeters going to 24. So that's sort of like a ×4 because the radius is squared. So that's just ×2 squared, ×4 here. And then height is what we're trying to find, so we don't worry about that. But we also have 1/3 here and no 1/3 here. So this is also a sort of ×3 relationship. Now, pi is fixed, the radiuses are fixed, this 1/3 is gone. How do we correct for all this multiplication for the volume? We need to correct it through h. So because we have a ×4 here, a ×3 here, then h must go a ×1/12 to reverse this volume multiplying, because the water is going to stay the same volume. Therefore, this h here is 18 centimeters. We multiply it by 1/12. That gives us 18/12, which is equal to 1.5 centimeters. So this is how we use ratios sort of to get the height right here. We could have also calculated the volume and then did a volume equation again to find the height, but I think this way is a little bit easier, right? So back to our answer choices. Oh no, not that one. Okay, back to our answer choices. So my answer is A. And then we can check, and that would be correct. Awesome. Eddie, do you have anything about this question?
Yes, I'm going to, I drew up the cylinder, a sphere, and a cone just to go over cool things. So there's a lot of good videos on YouTube that show you pouring water from a full cylinder into a sphere with the same radius and height, and then a cone with the same radius and height. So the relationship between the three is that a sphere is 2/3 of a cylinder. It fills up, if it's the same height and radius, it fills up the exactly 2/3 of a cylinder. And a cone, 1/3. And so if you look at the formulas, it's basically the sphere is 2/3 pi r squared h, and the cone is 1/3 pi r squared h. The problem with the sphere, though, is what's the height of a sphere? Well, it's just twice the radius, it's the diameter, right? So instead of adding an extra variable h in there, we made it easier by putting 2r, because that's what the height is. The height is just 2r. So that means you multiply that through, and you end up getting 4/3 pi r cubed. So it's less obvious that it's 2/3 of a cylinder, but that's where the formula comes from. So hopefully that clears some stuff up. Okie doke.
Wow, that's interesting.
Yes. Moving on to the next one. So we're hopping around problems if you haven't realized yet, but we're on to number 15. Okay, and by the way, I remember somebody in chat said there better be geometry. You got your geometry problem first thing out of the way. So, alrighty. Values for A, B, C, D are to be selected from the set of integers from 1 through 6 without replacement, which means no two letters can have the same value. how many ways are there to make such choices so that the two curves y equals ax squared plus b and y equals cx squared plus d intersect? And the order in which the curve is listed does not matter. So we're just looking for, different coefficients x squared plus b, cx squared plus d, such that we get an existing curve. Okie doke. So let's think about what this means. If I were to graph two parabolas, I'm going to have, they're all in the form of something squared plus x squared plus b. So they're all in the formula. I'm going to use functions. So f of x equals something times x squared plus some constant, right? So if you're familiar with parabolas, they're going to look something like this, right? And the thing is, what the coefficient in front here does is it stretches and I guess unstretches. It makes it wider. So for example, this might look like the graph y equals x squared. The graph of y equals 2x squared is a little steeper. And the graph of 1/2 x squared is a little less steep, a little wider, I don't know the word. But the idea is, since we can only put 1, 2, 3, 4, 5, 6 in here, the parabolas are going to be steeper and steeper and steeper, right? And so basically the idea is, and then finally, what this coefficient here does is it moves it up or down. So if I said +3, for example, I would be moving the parabola, let me do this. I'd be moving the parabola exactly 3 up. So I would do something like this, right? It'd move exactly 3 up, right? But we're not going to do 3 for now. And basically, what the idea is, we just want to look for any two of these such that, say, if I took 2x squared plus 3 and x squared plus 4, well, those intersect. How do I know they intersect? Well, basically, they look like they intersect on the graph. And that's what it means they have a solution. Okay, sorry. The problem asks for intersection. So what we could think about it algebraically is that they have a solution when you solve the equation. So what does that mean? I'm just gonna copy down the equations we have. We know we have ax squared plus b, and then also at the same time cx squared plus d. So these are like the values. These are the y coordinates in the graph. And then if they intersect, that means at some point they're gonna be equal. And solving, we can say that I'm gonna manipulate a few of the variables so that we have, actually, let's just put them all on one side. So a minus c x squared plus b minus d. So we know this equals 0. So if this equals 0 and we want it to have a solution, that must mean that, actually, wait, I'm going to put this on the other side. Sorry. So change of mind, and I'll explain why in just a moment. Oh, so that becomes a negative. So I guess I could write it as d minus b, but all right. So this is our equation, right? We want there to be solutions that exist. Well, the thing is, x squared is always positive. So whatever sign a minus c is, if a minus c is negative, that means this has to be negative. If a minus c is positive, then that means this has to be positive. Sorry, negative, or whatever. I forgot what I said already. Memory isn't doing me well today. But we just have to make sure that solutions exist. And so we just have to make sure that a minus c matches the sign of, I guess it would be easier if I said d minus b. So d minus b. And I'm thinking right now, isn't there a way to just pick any, so couldn't you pick any of the values and see if they're, so we know they're at the very most total. There's 6 times 5 times 4 times 3, which is 360. No, yeah, 360 total ways. So okay, that gives us a max, but that doesn't help us at all. So we have to figure out which ones don't work. I think in every single arrangement, isn't there a way, because when you pick any 4 numbers from 1, 2, 3, 4, 5, 6, I'm pretty sure that there's only like a certain amount of ways you can actually match it up. I'm doing this in a really weird way.
I have an idea. I'm just watching you. I was inspired by what you were doing. And I'm just like, it looks like they have to have the same sign. A
Yeah.
minus C and D minus B, and that feels like a half thing.
Oh, okay.
Does that help?
That's true. So basically, out of whatever, okay, I understand. So that helps a ton. Basically, if I pick any four numbers here, I can just pick two of them to be A and C, right? And so whether that's 1 minus 3 or 3 minus 1, that decides the sign for this one. And so whether it's positive or negative, that already decides the remaining two numbers. It fixes in place whether it's 4 minus 6 or 6 minus 4, because whatever it is, it has to match A minus C. So that means no matter what arrangement of four numbers I pick from 1, 2, 3, 4, 5, 6, I take two of them, assign them to A or C, doesn't matter. And then once I do that, the remaining are fixed, B and D, which means there's actually no choice for B and D, which means whenever I pick four numbers and assign them A, B, C, D, I can arrange these in any way, but I actually can't exchange B and D. Basically, B and D is fixed in place. And because I can't change these two numbers, exactly half of the values don't work. I'm not sure if well, Aiden, one of you guys can explain it.
I don't know if that's the answer. I haven't checked yet. That's
Is
my
it?
gut.
I think that I was trying to take a big shortcut by just doing that, but it's not.
Oh
Unfortunately.
no, I screwed up.
Maybe it's does it fix it twice?
I have an idea because, okay, this is a little bit strange, but I realized in the question that it says the order in which the curves are listed does not matter. So that's like another divide by 2.
Okay.
But yeah,
so
maybe
whatever
if you
A and
divide
C
that by
do,
2.
you flip it. Okay. That makes sense.
Wait,
All
so
right.
can you give a complete explanation now? Because I actually am still off by a factor of 2. So how are you doing this? Because that's exciting. If you did this and forgot the order and you got the right, and you got off by a factor of 2, because I'm off by a factor of more than that. So how do you get that? Could you explain that again clearly? Because that's good. I think you got it then.
Wait, Aiden or me? Sorry.
Either, because one
Aiden,
of you
go
has
ahead.
it, and I'm off by a factor of 2.
Okay, wait, sure. I will I'll get rid of this graph. I was originally thinking maybe drawing graph would work, but then it turns out this algebra is a little bit better. So just as Eddie did, we're gonna like look at the discriminant of these two things, and well, not discriminant in this case. We're just gonna see if there's a solution. Because if there's a solution, there's going to be two solutions. So if ax squared plus b, we intersect them, cx squared plus d, this is a minus c times x squared is equal to d minus b, and then x squared is equal to d minus b over a minus c. So the first condition here is that this thing has to be positive. So we can select any 4 actually. So if we do, there's 6 numbers here. We can select 4 and then put them in A, B, C, and D. So far we have 6 times 5 times 4 times 3 as our total. But we have a strange condition here that says the order in which the curves are listed does not matter. And it gives us an example. Basically, swapping A, B, and C, D in that exact order does not matter. So in reality, there are only this many possible A, B, C, D selections. That's like the total possible. And then now if we look at our condition in the question, the condition is for there to intersect. And the condition for it to intersect is that this number D minus B over A minus C must be positive. And then that's a 1/2 chance because D minus B, A minus C equal probability of being negative or positive. So we divide the total amount of possible ways by 2 because exactly half work. And then if we calculate this, then that's, okay, cancel this 2. That would be 180 divided by 2, which I get 90 actually.
That's right. That's the right answer. That's good.
Okay, wait, yeah, okay, so that's the right answer. Yay.
Okay. Great. Well, thanks for explaining that. So that's good. Yeah, I was off by a factor of 2. So I think we managed to solve this as teamwork, which is good. Meanwhile, I'll also say if this is the first time you've joined one of these live solves, in case you haven't figured out by now, none of us have looked at the problems yet, and that's by design. Well, I mean, we haven't prepared for this particular one. That's by design. We want to make sure that you can see how people would solve things if they look at it, and they have to think about it on the spot. That's the entire point. Also, if you're new here and you're wondering how in the world are some people able to talk, the way you talk is that you send messages in Zoom to something called chat relay. So you go and inside your Zoom, you choose who you want to write your message to, chat relay, whatever you send there, it will come here. And sometimes people write messages that the moderators will like and they'll somehow get stars. That's how that works. Yes, exactly. Like this. Thanks, Sophia, for demonstrating. And usually there's about a 10-second lag. That's only because in case there are really inappropriate remarks, we remove those. But in general, we found out that this is quite reasonable. So, okay. Yes, what I said about not completely appropriate remarks. Anyway, so things like that. But in any case, this is something we encourage you as we're talking. Feel free to say what you want to say. The other thing I want to comment is that we've gotten feedback before from our live solves where people have said, these look insane, they're going too fast. Well, we're going to be intentionally trying to be a bit more understandable today. So please, if you find that this is going slowly, please understand we're doing that on purpose to make it so it's as understandable to people as possible. Everyone at some point was trying to learn, and we want to make this understandable. Okay, great. I think I'm the next one, so I'm going to go. Got some words. Raven, Oscar, Aditi, Tyrone, and Kim play a card game. Each person is given 2 cards out of a set of 10 cards numbered 1, 2, 3 up to 10. The score of a player is the sum of the numbers of their cards. The scores of the players are as follows. Raven, 11, Oscar, 4, Aditi, 7, Tyrone, 16, Kim, 17. Which of the following statements is true? Okay, so first I have a lot of words, so I need to understand what's going on. I see that there are 10 cards, and I see how many people? 1, 2, 3, 4, 5 people. So if I have 5 people and 10 cards, well, I guess that means that, does everyone get 2 cards? Yeah, 5 times 2 is 10, I get it. And by the way, if you're making a comment about it being easy, I understand that for some people, these things are easy, but we also want to make sure that this is something where everyone can understand, especially if they haven't seen the question before. Some people here may have seen the question before. And by the way, I want to emphasize, whenever we actually really do teach our classes, we actually use this whole method to teach all of our online classes. We usually don't have a situation where people are all like already knowing what to do, because the point is that it's good to learn. Okay, now the score of a player is sum of the numbers on their cards. Okay, so I know that some sums of numbers add up to these things. Now whenever I look at this, I'm looking at it and saying, 2 numbers add up to 11. I've got a lot of choices. But when I have too much stuff here, I want to reduce my choices. I see that there's a number here called 4. And I think it's hard to make 4 as the sum of 2 numbers. Can anyone type into the chat? If I have different numbers from 1, 2, 3 up to 10, do you know how to get 4? I think there's only one way. Yes, thank you everyone in the chat, 1 and 3. So I know that Oscar has 1 and 3. Oscar, 1 plus 3. All right. Can I reduce anything else? The next thing I look at is I'm curious about the big numbers, because the small numbers I'm restricted. Anyone see a big number that is stuck? I see 17. I go for the biggest, okay? 17. How do you make 17 if you can only use the numbers 1 through 10? Well, I got 2 choices, don't I? So 17 is either 10 plus 7 or 9 plus 8. I wonder if I can split into these 2 choices and see what happens. Either 17 is 10 plus 7, or 17 is 9 plus 8. Does that help me? I'm just trying to go deeper now. And I'm trying, yeah, some people are saying this is similar to some problem. This is like maybe there are some various logic puzzles of how to put together numbers. So the next big number is 16. How could I make 16? Well, let me continue these cases. If 17 was 10 plus 7, could I make 16 somehow? Well, 16, that's 9 plus 7. But 7's taken. 16 is 8 plus 8, but I can't do 8 plus 8 because that uses 8 twice. So 16 is bad. That means that this case is over. I can't do any more of that. Oh, wait, I can. I can't do math. I can. Okay, sorry. Somebody said 11 plus 5, and I said, yes, it is. And then that's when I said I can't do math because it is 11 plus 5. What did I do? But you can't use 11. Why can't you use 11? Can anyone type into the chat? Why can't we use 11? There's a reason. Yes, thank you, everyone. It's only the numbers 1 through 10, so that's why. All right, so then I'm stuck here. There's no other way to make 16. So I have to be over there. That makes me happy. So 17 is 9 plus 8. And that means that 16, there's only one way to make 16 now, right? If I've gotten 9 and 8 eaten up, I think it has to be, is it 10 plus 6 is the only way? Yeah, thanks everyone for participating. 10 plus 6. Okay, I got lots of information now. Can I make any conclusions? So Oscar, okay, let's knock out things. Oscar has 1 and 3. Then there's no way that Rayvon has card 3. Actually, there's no way that Aditi has card 3. Okay. Meanwhile, who's 17? 17 is Kim. Do I know anything about Kim? No. How about 16? 16 is Tyrone. Oh, Tyrone, let's look at this. So I see people are going quite fast. I'm sorry, I'm not that fast. I'm going slower. I'm just looking at these things. 17 is Kim, and none of these say anything about Kim. They also don't say anything about 9 or 8, so that's not useful. But 16 is Tyrone. And so Tyrone gets 10 and 6, but there's a thing down here. I'm going to make my chat temporarily invisible because I think that we can rule out something, right? If we're saying that Tyrone is 16, Tyrone is 10 and 6, Tyrone cannot be given card 7. Let's use the pink. I'll put the chat back in a second, don't worry. So that's out. So now I only have 2 more possibilities to go and figure out. I'm going to go put the chat back on. Hi, everyone. Boing. Okay. Now what's left? Card 4. It looks like I need to know who gets card 4. Oh, that's the 7 person. How do you make 7? Wow, 7. So first of all, these guys are gone. Do I have enough choices for 7? Let's see. So how do you make 7? 7 is 1 plus 6. But we can't do 1 plus 6 because 6 is eaten up. Okay. 7 is also 2 plus 5. Okay, that's possible. 7 is also 3 plus 4. Could it be 3 plus 4? Why can't it be 3 plus 4? Why don't you tell me? Why can't 7 be 3 plus 4? There's a good reason. Yes, thank you, Bill, and a bunch of other people, because 3 is used. So it cannot be 3 plus 4. That means I only have one choice. 7 is 2 plus 5. Who is 7? 7 is Aditi. In that case, let's look. One of the, well, let me block the chat again. One of the things that's bad is that it says Aditi is given card 4. That's not true. And I think that means that the answer is that Rayvon's given card 4. Is that right? Do people like this? Yes, I know you're blocked, but that I had to take it off so you could see the questions, see the answer choices. Yes, I like logic choices too. It looks like I'm left with C. Is that right?
Yeah, looks good to me.
Yay! Did you guys want to add anything?
I think for multiple choice questions like these, especially where it's like, which of the following statements is true? A key piece of information is that not only is one of them true, but 4 of them are false. So double check that, like it's only that one that's true. And that can also like help you eliminate some cases as well.
Yeah,
Cool.
really, you don't, oh, okay, this is something, okay. So for questions like these, it seems very arbitrary. Like, how are you gonna know which specific 2 are going to be these? So what Professor Lowe did, I want to emphasize that you want to look at the smallest or the crazy big ones. So the crazy small, the crazy bigs. And then normally they'll be forcing like your conditions to a sort of edge. And then you'll gradually get more and more information. Awesome. Okay, I'll take the next question then. So, okay. A fair 6-sided die is repeatedly rolled until an odd number appears. What is the probability that every even number appears at least once before the first occurrence of an odd number? This question is a little bit scary at first because it technically could go on for an infinite amount of time. And if we try to think about casework, technically there are infinitely many cases. Like, what if we just had 2, 2, 2, 4, 2, 4, 2, 2, 2, 2, 4, 4, 2, 2. Okay. Like, I think that's going to be an issue because we can't do much casework here because of those edge situations. And we don't know exactly how long it would take for this first occurrence to actually happen. Okay, so that's hard. What if we could also have things like 2, 2, 4, 4, 4, 4, 6, and then our first odd. This would be satisfactory. But then on the other hand, something like 2, 2, 4, 4, 4, 4, 3 is bad because no 6 is here. So, okay. this makes me think of a sort of states idea. Like states is where we set variables for a certain situation and then the probability that it'll occur. So what if it's like we could set states like P of 2, P of 2, 4, P of, or even something like P of 1 even, which is the probability that our desirable outcome happens when we have 1 even in our list so far. We could also have something maybe like P of 2 even, and then our probability that we succeed if there are currently 2 good even numbers in our sequence. So if we had something like P of 1 even, well, 1/6 of the case we get an even number, the same even number. So 1/6 we still arrive at P1 even. And then there's 1/2 we hit an odd number, and in that case we failed. So that's 0. And then we have 2/6, which is 1/3. We hit P of 2 even. So then, okay, this is a little unclear right now. But basically, oh, I see it now. Okay, this is my thought process. When we write this sort of state equation right here, getting another of the same even number does not change anything. So in a sense, it's irrelevant here. It's completely irrelevant if we get the same even number. So what if we focused, okay, I'm not entirely sure if this is gonna work, but what if we focus only on the first occurrence of a new even number? So for example, we could have like 2, 2, 2, 4, 4, 2, 2, 4, 6, 3. In this case, in this desirable case, we could focus on the only one that matters, which is this 2 right here. This 2 and this 2 does not matter because it does nothing really. It's completely irrelevant because we already have a 2. It does not affect the impact here. And then 4 here is also significant. And then 6 here is also significant. All this doesn't matter because we already have it and it's irrelevant. And then the 3 matters, of course. So what if we looked at it that way? Okay, I hope this is gonna work. So suppose we start from nothing. The probability we first get an even number is 1/2. And then this part might be a little bit difficult. Actually, no, it might not be difficult. So ignore the rest of the 2's because they don't matter, honestly. But in the next new number, in the next new different number, what is the probability that it won't be an odd? It'll be a different even. So if we already got 2 here, then for the next different number, the choices are 4, 6, 1, 3, and 5. If we get 1, 3, and 5, we're done because not satisfied condition. So the probability it works here is 2 out of 5. And then we got 4, right? And then this doesn't matter here anymore. 4, 2, 2, 2, blah, 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 4. They do not matter. They're completely irrelevant. Okay, I have said irrelevant so many times now, but that's true because these numbers are just irrelevant to our situation. If we focus on the next different number, so we're looking at our sequence as a whole, the next different number, suppose we use 2 and 4 here, then the choices for the next different number is 6, 1, 3, and 5. So what is the probability we can still succeed? What's this next fraction I'll be multiplying here? 1/4. Yeah, I think it's 1/4 as well, because there are 4 choices for the next number that's different. And one of them is even. The rest are odd. If we get the even, we're good. If we get the odd, we failed. So that'd be a 1/4 chance. And then after the first 3 different numbers have all been even numbers, we're guaranteed that every even number appears at least once before the first occurrence of an odd number. So if we multiply this together, I get 1/20, which is C. Does this make sense?
I got it. I know you mentioned that you said irrelevant too many times, but it actually inspired me to go. I didn't know what I was doing, and then he kept saying irrelevant. I was like, oh, that makes sense. I did something very similar, but I used fractions the whole way.
How did
So
you do it? Wow.
basically, from the very beginning, you have to roll it even, otherwise you already lose, right? So 1/2 chance you roll it even, and from there, whatever even number you roll, if you roll that number, it's a reset. It doesn't matter at all. It's, in your words, irrelevant, right? So now the game says there's a 1/6 chance we reset and keep going, proceed as normal, nothing has happened, we've neither won nor lose. 1/2 chance we roll an odd number, which means we lose, and 1/3 chance we keep going. And since this part, the reset is irrelevant, we're looking at the ratio between 1/2 lose and 1/3 keep going, which in Aiden's example is basically the 3 odd numbers and the 2 even numbers. I just did it in the form of a fraction. And so comparing 1/3 and 1/2, that's 2/5 chance of winning. And I just did it by dividing the fraction here. And then from there, the game becomes the 2 numbers you roll even is a reset. Well, still 1/2 chance you lose and 1/6 chance you keep going. Same thing, exactly what you did, just as a fraction. And then multiply them all together, you get 120.
Wow. Okay. This question gets cooler by the moment. Oh my
This
God.
is
I just realized. Oh, sorry. Go ahead, Professor.
no, go on.
Oh, I was just saying, like, Eddie and I, basically what we're doing is that the question is giving us a whole complicated chain of things, and then we're just taking pieces and throwing them away, or resetting, in Eddie's words.
Yeah, so this is very interesting because actually when I saw this question right away, I was thinking, okay, let's do it in infinite series, because I saw people in the chat also saying infinite series. You can go and decide where you're going to go and put that first odd number. And then I thought that's still going to be messy. And I have a totally different way. And the totally different way uses inclusion, exclusion. But that's why I think my way is worse, because usually I'm doing inclusion, exclusion and getting the complement of the answer. And you're just multiplying. Yours is nicer. So what did I do? I was like, okay, my font is too small. But what I did is I said, let's make some events, some things that have probabilities of. The A event is called the chance that the first odd number comes before the first 2, right? And then I've got the B event, which is that the first odd number comes before the first 4. And then I also have the chance that the first odd number comes before the first 6. Now, if I think of this A, B, and C, these are like, this is like some kind of a Venn diagram. I've got the A, I've got the B, I've got the C, and I want to know what's not in it. I basically want to exclude, I want to know what's outside, because what's outside is that the first odd doesn't come before the first 2, and the first odd doesn't come before the first 4. Does that make sense? I think this is the opposite. This is the exact opposite of what you want, because what you want is the chance that every even number comes at least once before the first odd number. And so here's the cases where you fail. Like you fail because the first odd number came, but you didn't get a 2 yet, okay? So then I've got these 3 things, and I was like, I just need to go and figure out the probability of A or B or C, and then complement it. So my answer is going to be 1 minus the probability of A or B or C. And there's a way to find that out, because the probability of A or B or C is the probability of A plus the probability of B plus the probability of C, minus the probability of A and B, minus the B and C, minus the C and A, plus the probability of A and B and C all together. I wrote vertical bars because that's usually how we draw like sizes of sets when we do inclusion, exclusion, but it's really probabilities. And the reason why these are nice is because the probability of the event A, what's the chance that the 3 odd numbers all come before the first occurrence of each of the 3 odd numbers is before the first occurrence of 2. The way you think of that is if I want to know like the first occurrences of 1, 3, 5, and 2, well, I don't really know where they are. Here's my timeline. But wherever they are, like these are the first occurrences of those 4 numbers. And I haven't yet told you what those 4 numbers are. Like if I say these are the first occurrences of the numbers 1, 3, 5, 2, it's still symmetric. Like which one of them is, that's where 1 appeared first. That's where 3 appeared first. That's where 2 appeared first. That's where 5 appeared first. Those are all equal chance of like distributing among these 4 spots. And what's the only way that I could have that the first occurrences of an odd, the first odd appears before the first two, well, that's just looking at the very first term. First odd before first two, before first two means that the very first thing is just odd. The first of these 4 stars is odd. But those 4 stars, like the star here is either a 1, a 3, or 5, or a 2. So the chance that it's actually an odd number is there are 3 odd numbers out of 4. So that's why that's 3 out of 4. Did that sort of make sense? I'm just saying, like, if I'm looking at the first occurrences in my timeline, there's a 1, there's a 3, there's a 5, there's a 2. I don't know which order the 1, 3, 5, 2 will come in their first occurrences, but the only way that the odd one comes before, the first odd one comes before the 2 is that this is actually odd. So that's 3/4. So that's actually the first piece. And then the same logic will tell you if I want A and B, what's the only way I can, well, what does that mean? That means that the first odd number comes before the first 2 and before the first 4. So if I need the first odd number to come before the first 2 and the first 4, then I'm actually doing the same thing again, but now it's like there's also a 4 here. And if there's also a 4 here, then I have 5 unknowns. I don't know where they are. I don't know what they are, but there are these 5 first places that first place that the 1 appears, first place the 3 appears, and so on. And now what's the only way that I can have the first odd appear before the first 2 and the first 4? Well, that just means that the first thing here is odd. If I have the numbers 1, 3, 5, 2, 4, if I put a 2 here, then it's not true because the 2 appears before the first odd. So then the only way that you can have that this guy is actually odd, first of these, this is the same as the first of these 5 stars is odd, then that is 3/5. Because I have 5 different numbers that could go in the first star, and it's 3 of them are odd. And it's this way of thinking, what's the chance that the first occurrence of an odd number comes before the first 2 and before the first 4, that's 3/5, and before the first 2, the first 4, and the first 6, that's the 3/6, that's the 1/2. And then you just use the inclusion-exclusion formula, add these 3 minus the sum of these 3 plus that, and it worked. But that's just a very different way of doing the question. When I say it worked, I have to take the complement at the end. I have to do 1 minus. And I was very surprised when the answer came out and you guys did totally different things and it still worked.
That was really cool though. I learned a lot.
Okay. Who's next? Is it Eddie next?
I think so. All right, then I will head on to number 20. So number 20 says, in how many ways can the sequence 1, 2, 3, 4, 5 be rearranged so that no 3 consecutive terms are increasing and no 3 consecutive terms are decreasing? So basically what this is saying is that we can't have, for example, like 3, 4, 5, 1, 2, because in 3, 4, 5, it is always going up. And in 1, 2, and then like, actually this is fine. And we can't have, say, like 5, 4, 1, 2, 3, because from 5 to 4 to 1, that's decreasing all the way through. So right away, I know I can get the answer by drawing a tree diagram. I mean, the fact that there's only 5 numbers makes me think, oh, it won't take that long. And the numbers, I'm hoping it's not D or E. Like, this is very countable. I can count up to 18. I don't want to count up to 44. So I don't know. I can't think of a better way to do this. But let's just see how fast the tree diagram takes. You know what? It can't be that bad. And here's another thing, another reason why I know it can't be that bad is the amount of times I'm going to start. Okay, so we're going to count how many sequences work if they start with 1, how many sequences work if they start with 2. This color doesn't blend in. How many sequences with 1, 2, 3, and then here's the thing. I'm also going to count how many sequences would work that start with 4. But this is 1 away from the biggest number, and 2 is 1 away from the smallest number, which means that these should be the same amount of cases. The amount of cases that start with 2 should be the same amount that starts with 4. And then the same logic with 1 and 5. They're just on opposite sides of the spectrum, but they're symmetrical. The amount of cases that 1 works should be the same amount that 5 works, because you just flip every number. Almost like 3 is -3, and here like the opposite of 2 would be 4, because we're like 3 is the line of symmetry. It's probably not actual math terms, but hopefully you guys get the idea. So I'm going to first count all the sequences with 1. So with 1, I'm going to make my pen thinner so we can draw. So from 1, I can hit 2, 3, 4, 5. All of those are legal. But from 2 and on, this doesn't work. Because if I go 1, 2, and any other number out of 3, 4, 5, it's going to be always increasing. So that doesn't work. That's a no. So with that same logic, 1 to 3 must mean that it has to go to 2. Because 4 or 5, it would keep increasing. And so 4, if we don't want it to keep increasing, otherwise it'd be 3 consecutive numbers increasing, this has to be 2 or 3. And for 5, it can go to any other ones. 2, 3, 4. So now we just continue with our tree. From 1, 3, 2, we have to arrange 4 and 5. But if I do 2, 4, 5, it's going to be 3 increasing. So this has to be 5, 4. 2, 5, 4. So that works. We're good. 1, 4, 2, and then I have 3, 5 left. But I can't have 2, 3, 5. That's 3 increasing. So it has to be 5, 3. And then 1, 4, 3, I just have to put 2, 5 in some order. And I actually can go both 3, 2, 5 and 3, 5, 2. Neither of those make 3 increasing or 3 decreasing. So now we go on to 1, 5, 2, 1, 5, 2. If we go 1, 5, 2, 3, 4, that's increasing. So it has to be 2, 4, 3. 1, 5, 3 can either be 2, 4 or 4, 2. And if you notice a pattern, because 3 is in the middle, generally we can get 2 cases out of it. 1, 5, 4 can't have 4, 3, 2. So we'll do 1, 5, 4, 2, 3. So how many cases is that total out of 1? So that's 1, 2, 3, 4, 5, 6, 7, 8. So you got 8 cases for if it starts with 1. And because we know that 5 is just every number here, but like on the opposite end of the spectrum, 5 is 8 cases as well. Let's look at 2. So how many cases will I have for 2? We can start by going to all of the numbers because that's still legal. And then from there, if we go 1, 2, oh, sorry, not 2, 3, 4, 5, we keep going. So 2, 1, that can go to any of 3, 4, 5. But the problem is, if I go 2, 1, 5, actually there's no problem. Never mind, scratch that. So 2, 1 has to go 3, 5, 4. Otherwise, 3, 5, 4 is always increasing. 2, 1, 4 can't be. Oh, wait a minute. I've made a lot of mistakes because 1, 3, 5 is not gonna work at all. I hope I didn't make a bunch of these. Now I have to go check my work. This is why casework isn't always the best plan of action. Yeah, so like this 1, 5, 3, 2 doesn't work because we're going 1, 5, 3, 2. So I've only been considering the last number and the next two. You have to make sure you're getting the last two. I did not do that. So this 1, 5, 4, 2 does not work either. 3, 4, 2 is fine. 4, 3, 5 is fine. 4, 3, 2 is not fine. 1, 4, 2, 5, 3, that's fine. 1, 3, 2. Okay, so I lied. 1 only has 5 valid cases. So now let's keep going. So 2, 1, 5. For 2, 1, 5, I can either go 2, 1, 5. Actually, no, I have to go 2, 1, 5, 3, 4 because 5, 4, 3 doesn't work. 2, 1, 4. Well, it can't increase after 1, 4, so it has to go down to 3, and then 4, 3, 5. Then 2, 3, it can go 1, 4, 5. Wait, we'll just see. It can't go to 4 or 5, otherwise it's always increasing. And it can't go to 1, 4, 5, otherwise it is always increasing as well. So that's the only one that works there. 2, 4. So it can't increase, so it has to go to 1 or 3. And from there, 4, 3 can't go down, so it has to go 5, 1. And 2, 4, 1 has to go 5, 3. These are all good. 2, 5 is gonna be. We can go down, so any of those work. 1, 3, and 4 all work. But 5, 4 is gonna decrease, so that doesn't work. 5, 3 has to go up, down. This has to go up. Oh wait, this has to go up and down. Okay, so for 2, we have 1, 2, 3, 4, 5, 6, 7 cases. Ooh, these are consecutive odd numbers. I'm wondering if there's a pattern. Okay, I think I cleaned up all my mistakes there. So finally, we get the 3 case and we'll be done. So that's covering all main action. This will probably be, actually, I don't know. I don't know what this will probably be. So final case, it is very tedious and, very boring, but it is a way that works. I hope. We'll see if I get the right answer. It works if we get the right answer. So 1 can go to anything. So 2, 4, and 5. 315 has to go 2, 4. 314 has to go 2, 5. 312 has to go 5, 4. Oh no, that's increasing all the way. So 2 actually doesn't work. So 3, 2 can't be 1, so it has to be 4 or 5. 3, 2, 4 can't be 5, so that's to be 1, 4, 1, 5. 2, 5, that can be anything. So actually, no, it has to be 1, 4. And then finally, 3, 4, I'm just going to fill in the rest of the table. And then basically, I think another reason why casework works is because a lot of the things fall in place. Like, for example, at the third step, I'm already at only one possibility for the rest of the number. So it's another like reassurance of like, okay, maybe casework isn't going to take that long. Obviously, if you can think of a better way that's going to save you all this time, then 100% go try that. But I was not able to come up with one. So this is why we are crunching away at a bunch of numbers, right? Well, 5, 4 is always going to decrease. That doesn't work. 5, 2 has to go up. 5, 1 can go anywhere, but 4, 2. Okay, so that means I'm getting 1, 2, 3, 4, 5, 6, 7, 8. 8 cases. 5, 7, 8. This is they're all very close. But adding all of these up, you get 24 plus 8, which is 32. That is an answer choice. So that makes me relieved. But whether we're right, it's not the biggest answer choice. So there's still a possibility it's 44, but I'm getting 32.
Let's find out. Let's find out.
Okay, let's do the big reveal. Drum roll. Let's go.
Yes, it worked.
It does work. It does work.
Okay. Actually, I was thinking about this while you were doing it. So I had the luxury of just watching Eddie do it. And then it's much harder, by the way, to do the problem when you're like right there doing it and all the people are talking to you and you're supposed to come up with something. But as I was watching that, I was also noticing there was some kind of a pattern. Like, first of all, I couldn't understand what this means. 3 consecutive terms are increasing. No 3 consecutive terms are decreasing. That didn't sound nice. And then I just started trying to look at the things that, you know, like Eddie was drawing the tree diagrams. They look like wiggles. That's all that means. So that very complicated no 3 consecutive increasing, no 3 consecutive decreasing just means it's either an M or a W. It took me a while to figure that out. And in that sense, it's sort of like as you start listing things, you notice something. And by the way, if you don't know how to start a problem, go ahead and start listing things because then you'll notice something. So now I was like, come on, how hard can this be? Just count the number of M's or the W's. Turns out it was harder than I thought. So then, okay, how do you count M's and W's? Then I started thinking, well, first of all, there's an M or a W. So for symmetry, I'll just count the M's. Is that okay? Because I'll just count the M's and times 2. And then I said, that's it. I'll eliminate the answers that are odd. Drat. They thought of that. Okay, I was hoping that there would be only one even number, but that's not true, and that didn't help. So I said, okay, so it'll be 2 times something, right? And it'll be 2 times the number of M's. So I just put this 2 here. The red 2, this is like M or W. Okay, well, given that, then I started thinking, what else can I do? Then I started thinking, where do these numbers go? And I looked at the top, you know, like how Aiden said earlier when you were doing that other problem, like look at the big numbers and the small numbers. And so there's only 2 peaks. So I thought maybe that's easier to think about the peaks than the valleys because there's only 2 of them. And since there's only 2 peaks, well, I realized that the 5 has to be one of the peaks because 5 is the biggest one. So the 5 is either the peak on the left or the peak on the right. But by symmetry, it's the same number of M's where it peaks 5 on the left as it peaks 5 on the right. So there's a 2 here times 2 where I'm just going to say that the 5 peak is the left one or the right one. There's only 2 peaks in the M. Then suddenly my number of cases reduces by a lot because then I said, okay, suppose that's the 5 and it's an M. I like the other big number called 4. I only have 2 places I can put the 4. One place to put the 4 is the other peak. Obviously, I mean, it's a peak, so high number of 4. Actually, at first, I only thought it was this one. I thought that was the only one, and that would be scary because there's a tricky answer here of 24 to go and catch you on that. So remember, I'm going to times 4 my whole thing, and that actually leads to a wrong answer. But you see, there's 2 ways you can put the 4. One way to put the 4 is on the second peak, but there's another sneaky way you can put it, which is out on the left, right next to the 5. Actually, does anyone want to type into the chat? There's a reason you can't put the 4 here. Do you know why you can't do 5 here and then 4 here if you want an M? There's a really good reason. If this is 5 and then this is 4, well, those are the two biggest ones. They're already eaten up. So actually, then whatever you put here is not going to be an M. It's going to go down. It's like you put the two biggest ones right next to each other, and everything else is just, it's all downhill from there, right? So not all downhill from there. That's the wrong way of saying it. But the right way of saying it is you've got a 5 and a 4, and whoever is next to the 4, sorry, it's going down, right? So that's actually how you know the 4 can't go here. And you can't put the 4 here also, because if the 5 is there and you put a 4 here, well, something's supposed to go down to 4. What goes down to 4? Only 5. Actually, that's probably the easiest way to put it. Once the 5 is eaten, the only thing that can go down to a 4 is a 5. So the 4 is either here or it's there. Now I've got two cases. So now let's finish it. If this is a 5 and this is a 4, there's only one choice for what goes there. Does that make sense to people? It's a 5 and a 4. Those are eaten. And now I have this thing which is supposed to be one remaining mountain. And I have 1, 2, and 3 to play with for the mountain. If I have 1, 2, and 3 to play with for the mountain, then 3 is the peak of the mini mountain. So that's 3. Now, why did I write two ways? Can anyone type into the chat? I'm saying that the 4 is here, the 5 is there, the 3 is there, and I say there's two ways to finish. Yes, thanks, Bill. It's either 1 and then 2, or 2 and then 1. Those are the same. It's either 1 and then 2, or 2 and then 1. Yeah, you could reverse it. So I said this where there's a 5 here and a 4 to the left, that case, two ways. And then the only other case is a 5 here and the 4 is the other peak. By the way, I'm stuck in this case already of it's either an M or a W. I'm calling it an M. The 5 is either on the left peak or the right peak. I'm putting it on the left peak. Okay, so I'll do 4 times whatever answer I get. And the last case is 5 here and 4 there. So why did I write 3 factorial equals 6 ways? What does that mean? Anyone want to type into the chat? 3 factorial equals 6 ways. Why am I saying that? I'm saying the 5 is the first peak, the 4 is the second peak. Aha, yes. Good, I see a bunch of people saying, because there are these 3 lower numbers, the 3, 2, and the 1, and they can be rearranged into any way that I want. So there's 3 factorial is equal to 6 ways of rearranging the bottom numbers. So now I got this. Let's finish the problem. So it's like, there's 2 ways to do that case. There's 6 ways to do that case. So 2 plus 6 is 8. And then finally, I have to multiply by the things I pulled off at the beginning, M or W, and then the 5 peak being left peak or right peak. That's the 2 times the 2, and then the 8, and you get 32. So that's another way to get to 32. But I had the luxury of watching Eddie. So I'm not sure I could have come up with this like directly if I was on the spot.
Yeah, I also had the luxury of watching Eddie, but I was taking a different approach, like a completely different approach. So sadly it did not work, but I'm sure it's possible to work. But what I did, I was being systematic and inspired by Professor Lowe's solution to the last question. I was doing complementary counting here because no 3 consecutive terms, right? There's 1, 2, 3 of them. And then what if there's like, we're counting at least 1 consecutive term and then we subtract it from the total 120. So I was doing this and the first case is easy. There's only 1 rising, that's easy. The second one is easy as well. But in the third case, it becomes complicated because, well, not complicated per se, but about as complicated as the original question. It's basically, I was stealing Professor Lowe's arrows. Basically, you go up, up, and then down, down for 2 of them. One's going up, one's going down. So it starts getting a little bit complicated, but this is when you have to decide, should I list it a way that I know will work and won't take too long, or should I risk trying to do something like this, which may knock out too much of my time? So I chose this way and it knocked out my time and I still didn't solve it yet. But at one point, it's a good idea to probably just switch. Okay, these numbers aren't that big. I'll just list them or do casework. Or even better, do Professor Lowe's way of going up and down and up and down.
Yeah,
So,
I also want to add, like, I mean, if I was actually doing the contest and not trying to do a live solve, I might also just be like, okay, quick, let's just try to solve this. There's only 120 total. We'll get it. It's just because I was watching Eddie and I was like, Eddie's already doing that. So can I come up with something else? But that's all. But that was good. That was good. Actually, it's interesting. Eddie also got the right answer. So it shows that if you do casework carefully, it really works. With that, I see that we've hit the time. It's 9 o'clock and that's when people usually need to go. So we had a lot of fun. I hope that you guys had fun. There will be one more of these sessions next week. And by the way, if you liked what you saw here, oh yeah, thanks. Actually, Aiden just pointed out we got something at the end. So let me just quickly go here. Right. And if you like what you saw here, we actually run all of these as live online classes in a way which is much more systematic. I do want to emphasize what you saw here was done quickly because somehow there's a lot of a live audience here, which everyone was trying to do as many questions as they could quickly. However, whenever we think the best way to learn something is to be able to learn it where you sort of systematically go through and learn all of the key components. And so if you're interested at all in that, these are all of the live classes that we happen to run. And that's all on live.poshenlo.com. We're very happy to teach all of these in the way that you just saw, which is where there's a lot of interaction with the audience, like what you just saw, and also where it looks pretty good. That's actually our objective. In any case, we'll see you next week and have a good week. Take care. Bye-bye.
Bye, everyone.
Thanks for coming.